But now it's time for today's session, and I'm very pleased to introduce Mark Hamilton and Jill Milton of NVIDIA. Mark and Jill, can you please come online? Mark, great to see you.
Hi, Jake. Good to see you.
And thank you and Jill for being with us here today. For those online, this is truly a global community, and Mark is actually connecting from Singapore for a session today. So thanks for staying up late for us, Mark.
Thank you for having me.
I'm not sure if it's late or early here, but yeah, it's great to join.
Well, I'll turn it over to you guys, and I'll go on audio and video mute and let you two take it away.
Okay.
So great. So welcome, everyone. This is Mark. I'm happy to be talking today. If I tilt, I just had my camera in this position for the intro, so Jay didn't see what T-shirt I was wearing, but I'm traveling. This is my I'm in my, let's see, 5th city in 10 days, and Jay called me up about 2 months ago and said, "Hey, we're doing this new podcast, and I'd love to have you come and join us with Jill, and here's the date." And I looked it up in my calendar, and I said, "Well, this is going to be the last day or the last morning is about to head home, and it's going to be middle of the night. But Jay, I'll go ahead and do it for you." So I've known Jay for a long time. I had to look it up. One of the very first HPC systems we built was in 2008. So Jay and I were working together at 2 different companies then. Jay was at TAC, and I was at a company that's no longer around, but we built the 7th largest supercomputer in the world, the TAC Ranger system. Jay mentioned he is at TAC, Advanced Computing System, Texas Advanced Computing System. And Jay, just for you, I happen to be here all the way in Singapore, and I didn't plan this, but you know, I was looking in my suitcase yesterday and seeing what clean clothes I had and I could wear, and I found this TAC Lone Star T-shirt. So this is Lone Star 6, which is a little bit more recent. Lone Star 6 happened to be a system with NVIDIA's Ampere A100 GPU technology. But even back when Dell worked with you, worked with TAC to build the Lone Star 6 system, supercomputing was really not being done in the cloud. There were certainly enough GPUs in the cloud, even back when Lone Star 6 was built. There were more GPUs in the cloud than there were in large supercomputers like the Lone Star system. But they weren't a supercomputer. They weren't configured the right way. They didn't have the right networking, and you just really couldn't do supercomputing work. And over the last couple of years, of course, that has all changed. And what's driven that change is the emergence of AI. And of course, those of you who do any work in AI on Google Cloud and really focus on what the infrastructure is, you recognize that AI is an HPC workload. Very high communication, both within the node and across nodes, high performance nodes, high performance storage. And Google Cloud, you know, today goes through GCP, brings all those technologies together. So as a result, it ends up being an amazing system for HPC, AI, and quantum computing. Jay, if those of you know him, know that quantum computing has been one of his passions. And so we'll talk a little bit about what NVIDIA is doing with GCP in all of these areas. So let's go ahead and get started. Advance here. So first, I'm going to talk a little bit about NVIDIA and the GCP partnership. I have Jill here for the Q&A. Jill is one of our account managers that supports Google and works with Google at NVIDIA. I thought I'd put right up front, and this is for Jay, talk a little bit about quantum computing and what GCP is doing with NVIDIA in quantum computing. Then talk about really how NVIDIA solutions in GCP are really bringing together state-of-the-art supercomputing in the cloud. And then finally, talk a little bit about the intersection of AI and HPC. So again, you can, and these slides will be available afterwards, and you can read what Thomas Kurian, CEO of Google Cloud, and Jensen Huang said at Google's one of Google's latest events. But you know, a lot of people, Google was one of the first clouds to deploy GPUs and has some of the longest history there. You say, well, you know, what does that mean, a partnership? Is Google just buying GPUs from NVIDIA and putting them into the cloud? We have hundreds of engineers across NVIDIA that work with Google in ensuring that those GPUs in GCP are really state-of-the-art and bring you that supercomputer performance. It, of course, starts at the hardware. As you know, Google develops their own servers. So our hardware team works very closely with Google to design the servers using that Google uses for their GPUs. But high performance computing, AI, and quantum are, of course, not just about the GPU, not just about the server. It's about the entire supercomputer. Those of you who worked at supercomputing centers know supercomputers in the past took years often to develop. In again, some of the largest supercomputers in the US have taken a year or more to deploy. So after we design the servers, we design the infrastructure, we then work closely with Google across the entire software stack. This is an area where even after the systems come online, we continue to improve performance. If you look at NVIDIA's Hopper H100 GPU technology in Google Cloud today, it's performing often 2, 3, 4, or 5 times faster than the same exact GCP instance did when the first H100s were deployed. You say, well, it's the same exact server. How is it possible that the same exact server performs 3, 4, 5 times faster 2 years later? What computer gets better over time? If you have a laptop computer, you know that over time it gets slower. Every time you upgrade the OS, more features and it slows down. And an NVIDIA-powered server is just the opposite. And that's because we continue to work to optimize the software across all levels, including the cloud software with Google. So anyhow, very close partnership. Let me tell you a little bit about what we're doing today. Today, of course, Google is right in the middle of their Blackwell rollout. I'll talk a little bit more about it. And today, NVIDIA engineers are sitting in Google data centers with Google, actually bringing up the first Blackwell supercomputers in Google Cloud. Google's posted some pictures of their first servers that they have. And again, that technology will give a roadmap, will be coming online later this year. So super excited about that. How does Google Cloud compare with other NVIDIA supercomputers? Today, my team is installing about 100 different supercomputers around the world, and multiple of those are actually in Google Cloud, and every one of them being installed exactly the same way. How do we measure? When Jensen asked me, Mark, how's it going with GCP? How's it going with those other customers? There's 3 things that I report to Jensen, and I'm sure makes its way over to Thomas. We talk about 3 things. One is time to first train. From the time NVIDIA's GPUs show up in the GCP data center, how long is it before those systems are physically installed, the GCP software is installed on top of them, and they're available to go for a user to access and rent through the cloud? Across those 100 supercomputers that we install, our average is about 3 weeks. this is just amazing. And if you've ever built a supercomputer, you know, that number can be 3 months, it can be 6 months. Some supercomputers take a year or more to bring up. So how is it that NVIDIA can work with GCP and bring up a new supercomputer in simply 3 weeks? It's because standardization and really having a common reference architecture and working with Google on that reference architecture. Second thing that we measure is availability. When we deliver 1,000 GPUs to GCP, we install it, we stand it up. What's the availability? As you know, if you've ever set up a supercomputer, if you've ever rented a large number of systems in the cloud, you don't get 100% availability, right? You'll have a node failure, you'll have component failures. You go through, you file a trouble ticket, you get that system replaced. NVIDIA is averaging about 97.5% availability at time to first install. Now that may not sound great, but again, 97.5% availability is far above the average of most systems and most cloud infrastructure. So a lot of work we do with Google to get to that. And finally, performance. Again, our benchmark is our internal supercomputers that we run at NVIDIA on-prem systems set up with our software stack. And when my engineers are working with GCP in setting up a cloud, we don't leave until we're within 1 or 2% performance of that system. So again, those 3 things coming together with NVIDIA and GCP, giving you access as soon as the nodes are available, giving you high availability of the infrastructure, highly available infrastructure, and giving you that optimal performance is super, super important. And you can look at another technology or a different cloud, and if they're not meeting those 3 things, it adds up quickly to 50% or more of the cost. So again, a lot of people are always saying, well, what's the node cost for, you know, what does it cost to rent this node per hour, and compare it to sort of cut on a dollar per hour basis. And that's probably the wrong metric to compare on. You really need to start looking at the throughput. How much work can I actually get done for dollar that I spend on that AI or HPC supercomputer with Google? So let's talk a little bit about the different offerings that we have. I'm not even going to go through, we'll give some more details, but there's all sorts of different offerings that NVIDIA has of different, that Google has of different instance types. And those include, of course, the latest Blackwell architecture. The A4 systems have been announced. As I said, they'll be shipping as we move into this year. All the other instances below that on the left, the A3 Ultra just went online with our H200 GPUs, the A3 Mega, and then some of the older G2 and A2 instances available on GCP. But of course, it goes beyond the hardware. We talked a little bit about how NVIDIA works with GCP to actually set up that hardware. It also goes into really deep integration of NVIDIA software across Google's different cloud offerings. Of course, Google Kubernetes Engine is available across those systems, and NVIDIA works to integrate NVIDIA's SDKs, the NVIDIA inference microservices, in all of the right configurations to make sure that those GPU instances live as first world instances within Google Kubernetes Engine. There's a Google Cloud Runtime, where again, our NVIDIA inference microservices are available. And of course, in Vertex AI, right? If you actually, of course, people know who do AI on Google Cloud know about Vertex AI, but Vertex AI has all of NVIDIA's SDKs and softwares integrated inside of it. And anyhow, going on through the stack there. And then finally, if you start on-prem, or you start in computing, all of NVIDIA's software stacks are NVIDIA inference microservices, NVIDIA AI enterprise software, and of course, even NVIDIA's DGX cloud. Now, a lot of you may not be familiar with NVIDIA DGX Cloud. So, well, wait a second. I thought this was about GCP Cloud, not NVIDIA DGX Cloud. NVIDIA DGX Cloud is actually an offering that has all the NVIDIA software optimized and is purchased directly from NVIDIA, but actually runs on top of GCP. So that means it's available in the NVIDIA marketplace. It's available in the GCP marketplace, and you can purchase it directly through that marketplace. Of course, and that runs on the same GCP instances that are, of course, available directly from GCP, but an offering that combines all of that software packaged very similar to NVIDIA's on-prem DGX solution. So before I go into quantum, I want to talk about a little bit about the GCP's most advanced offering, the A4X. They'll release with NVIDIA's Blackwell platform. When NVIDIA releases a new GPU these days, we don't just talk about the GPU chip. We talk about the entire architecture. This image actually shows NVIDIA's DGX GB200. Again, the technology underneath all of the components of this server are exactly the same as what Google's deploying in their instances. And again, Google's posted online some of their pictures, but those pictures are on Google's site. I didn't want to go through and copy, but I'm sure Google will be posting additional pictures as they bring online their systems. So the first thing is, when we talk about Blackwell and the GCP A4X, we talk about it as the NVLink 72 technology. So one of these racks that you see referred to here in the image is called the Blackwell NVLink 72 system, GB200 NVLink 72 system. Wanted to pull out and sort of talk a little bit about what you see in this image. First of all, this is not a single server with 72 GPUs. It's actually a lot more complex than that. Each rack, each NVLink 72 system actually does have 72 GPUs in it. And it's comprised of 18 different compute trays. And the compute trays in here are shown in green at the top and bottom of the rack. And there's a close-up of the compute tray on the right-hand side. The compute tray is actually the server node. And the server node has inside 4 different B200 GPUs. And those 4, each of the every 2 B200 GPUs is connected to a Grace CPU, hence the Grace Blackwell. Within the compute tray, each CPU is connected to those 2 GPUs with our chip-to-chip NVLink. And this is one of the big innovations that goes beyond Blackwell into that GB technology architecture. So this is the first time that the 2 GPUs in this case, the 4 GPUs in the compute node, every 2 GPUs have direct access via chip-to-chip NVLink to that CPU. You say, well, that's great. NVLink isn't new. It's been around for several generations now. So what's so great about putting the CPU on NVLink? Because now the CPU is on the same NVLink via the chip-to-chip interface as the GPU. It means that the GPU has cache coherent access to all the memory on the CPU. And as a reminder, right, our GPUs use high bandwidth memory, and they have typically, compared to a CPU, relatively small amounts, depending on the instance type, 80, 144 gigabytes of memory. A CPU, of course, can have half a terabyte, a terabyte or more of memory. So why is it that giving the GPU NVLink access to the CPU memory is important? If you've been programming in CUDA, in programming HPC applications for a long time, you know, that one of the, that in the past, to write a CUDA application that ran on the GPU, you'd have to go through and copy your memory, copy your data from the CPU over the PCIe bus to the GPU before you started running your subroutine or your kernel on the GPU. For the first time with the GB architecture on GCP, you simply can start running your code on the GPU and it can cache coherently access the memory on the CPU. This dramatically lowers the bar to entry of getting high performance out of the GPU without having to copy that memory over. Now, obviously, for the highest performance or after you're using memory for a long time, it will migrate over or you can manually place it over on the GPU. But it means that by simply having one subroutine, one part of your application available on CUDA and running on the GPU, you can get that very high performance. Of course, in the AI space, where so much of the code is in cuDNN and other NVIDIA libraries, that's been optimized to run almost entirely on the GPU. Another advantage of this is power efficiency. You say, well, of course, Mark, I read about how, you know, Blackwell is more energy efficient and Grace is an ARM-based technology. ARM is well known for its power efficiency. How does putting the two of them together help with energy efficiency? It has to do with the ability, you know, any server is limited by power. Its servers have power supplies. You have a certain amount of power that flows through the system and is shared with the CPU in the GPU. In a traditional GPU server, when you have a CPU, PC connected to the GPU, they live in two different power domains. So the system has to, ahead of time, determine where to allocate power. It may say, I'm going to give 100 watts to the CPU, I'm going to give 700 watts to the GPU, it's got 800 watts available for the compute, and you can never change that, or you certainly can't change that dynamically. Well, of course, depending on the application, every application is going to have different amounts of serial and parallel code. With the GB architecture, because that Grace CPU and the two Blackwell GPUs are sitting on the same PCB, being fed by the same power controllers, NVIDIA is able to dynamically shift power between the CPU and the GPU. So as an application first starts, it can go in and give maximum power to the CPU. So for instance, you're running some serial code, starting up the application. As you get into running your HPC or AI kernel, the CPU may be much less lightly loaded, and you want to give maximum power to the GPU. And with the GB architecture, you can the system will dynamically shift power back and forth on almost a cycle-by-cycle instruction between the two processors. So again, all sorts of unique characteristics of GB200 to increase power, to increase performance of the system. What about NVLink? It's called NVLink 72. Well, all of the earlier A3 and earlier instances on GCP, and in fact from NVIDIA before the GB architecture, the maximum number of GPUs you could put in one NVLink domain was 8. You had our HGX server, which is synonymous with AI and HPC computing, provided by every OEM in every cloud, and that was the maximum. And after, if your application was larger than 8 GPUs, you had to go through and connect them with high-speed networking. And of course, you know that training and even running deep neural networks in generative AI applications today can take thousands or even tens of thousands of GPUs working together. So how do we get 72 GPUs all talking via NVLink? In the HGX architecture, the 8 GPUs are connected with NVLink switches within the server. On the NVLink 72 architecture, and in this particular diagram, if you look at those two middle rows show the racks turned reversed. And so you're looking in the middle, in the back of the rack there. You actually have over 2 miles of cables, of copper cables running through the rack that are connecting all the GPUs and all the CPUs in the rack via NVLink. So you have direct GPU to GPU NVLink connections through the NVLink switches of all 72 GPUs. So now you think about that and you say, well, I have 18 servers in the rack, each with 2 CPUs and 4 GPUs, 18 servers, 18 versions of the OS, 9 NVLink switch trays that connect all those GPUs. I rent that as one instance from GCP and I fire up my application. How many months of programming does it take to partition out my application and get it to understand how to connect everything with NVLink? Well, of course, that's the beauty of NVIDIA's technology. At lower levels of the stack, primarily at the NVIDIA NCCL, the NVIDIA Common Collectives Library, is the software that understands the topology, understands how the GPUs, 4 GPUs are connected within the compute tray, understands how the 18 compute trays and 72 GPUs are connected, then understands how it all comes together across the network. And of course, NCCL is incorporated into cuDNN. cuDNN is used by TensorFlow, JAX, or your other AI training framework. Of course, it's available on the cloud. I know there's some questions rolling by in the chat. We'll go ahead and answer those at the end. So that's a quick overview on the GB200 architecture. Again, the beauty of AI, high performance computing, and quantum computing all run great on the same GCP instances. And so quantum computing, so I'm talking about a GPU. How do I suddenly switch to quantum? And how do the two of those come together? Unless you're working in quantum computing today and working with NVIDIA technology, you probably don't understand. And so I'm not here today to announce a new NVIDIA quantum computer. NVIDIA isn't building quantum computers. But if you're working on quantum computing today, you're probably using NVIDIA GPUs. And so this is the problem. You've all read how there's multiple manufacturers today in many startups that don't have product yet shipping that are working on quantum computing hardware. The state of the art, the largest quantum computers in the world today are less than 100 qubits. To run applications, to run quantum applications, you need at least 1,000 or more qubits to actually run any sort of real application other than toy problems. And so the question is, how, if you're a researcher and you're thinking about how do I develop an application for a future quantum computer, once they're commercially viable, once they get to 1,000 or more qubits, how do you do it if you only have less than 100 qubit systems available? And how do you do it with Google Quantum AI and NVIDIA? And there the answer is rather simple. You, of course, can't run on a physical 1,000 qubit system. They don't exist in the world. So if you want to do research, come up with some new quantum algorithm, you have to simulate a quantum computer. And NVIDIA cuQuantum is a software from NVIDIA that lets you simulate quantum computers. So again, this is available today as a virtual image on GCP. And so you can go in and make this available. And again, these are a number of different institutions around the world that are working with cuQuantum. today. So you develop your quantum algorithm, you have a quantum simulation framework, and that framework is then running on cuQuantum, running on your GCP instances. So why will the GB200 and why do the current A3 and other current generation GPUs, why are they so good for quantum? To simulate a large qubit system is a classic HPC problem. You, of course, need many, many GPUs, so you need a high-speed network connection. And again, with nickel underneath cuQuantum, it optimizes the connectivity. It takes advantage of the NVLink when that's available, and then goes out to the high-speed network. Second challenge is, again, as larger and larger QPU or quantum computers become available, how do you actually connect them to other software? As you know, quantum solves a very narrow class of problems. Those classes of problems that it solves, it's going to solve many, many times faster than any CPU or even any GPU. But just like the GPU was an accelerator to the CPU, we believe that most quantum architectures are based on the fact that that quantum computer will essentially be an accelerator to the classical supercomputer, where parts of the application that are not a quantum algorithm run on the traditional supercomputer and the rest run on the quantum computer. So how do those come together in the cloud, and why is the cloud a perfect environment for it? So again, NVIDIA has a technology called CUDA-Q. And CUDA-Q is the libraries, the programming models, the tools, and the infrastructure to let you start by simulating on cuQuantum, on GPUs, and then physically connect that GPU infrastructure via a high-speed network to your QPU hardware. So again, you'll be hearing in one of the next presentations, GCP's roadmap for actually rolling out quantum hardware. But as that quantum hardware rolls out in Google Cloud, you'll have instances that combine GPU instances on one side, connected via high-speed networking to those QPUs. And of course, just like when NVIDIA introduced CUDA in 2006, CUDA was that glue technology, was that library that let you connect the CPU to a GPU from the programming level. CUDA-Q is a technology that will let you connect your GPU server to the QPU hardware. So again, we're working very closely with Google to roll this out. And in fact, underneath is Google will offer many different types of QPU hardware. So of course, NVIDIA is working with all the QPU hardware providers to make sure that CUDA-Q is optimized on that hardware. So very, very exciting about the upcoming plans with CUDA-Q. And while this doesn't exactly this isn't related to quantum computing, but everyone believes that one of the classic problems that quantum computing will be very good at is encryption. And of course, if you're good at encryption, you can be very good at the reverse, or decryption. So of course, if you're any financial institution or other institution that uses encryption and relies on encryption for the safety and security of your systems, the challenge is that future large quantum computers hold the promise of being able to effectively outdate all of the existing encryption algorithms. Now, don't worry and go withdraw all the money out of your bank account today. There exists post-quantum encryption algorithms. These are encryption algorithms that have been developed over the last decade that will not be decryptable with a quantum computer. And these are existing algorithms. I list some of them up there. And of course, well, current day encryption has been optimized to run on CPU hardware and can run, and of course you can do encryption on the GPU as well, but most encryption today is done on CPU servers. By using running a post-quantum encryption algorithm is much more computationally intense. In most cases, you can't run it cost effectively, power effectively, or fast enough on a traditional CPU server. So we've actually developed libraries called our CUDA or cuPQC has taken all of these quantum safe encryption or post-quantum encryption algorithms and embedded them into the libraries. So NVIDIA today is working with many of the providers of encryption software for financial institutions, others, and helping them rewrite their algorithms, often on GCP using our cuPQC software. So again, all available today on GCP. So I'm going to finish up here and just go through a little bit. What are the current GPU families on A3? I'm not in marketing, but GCP always gives some nice, easy to remember names here. A3 High, A3 Mega, A3 Ultra is in many cases larger numbers, or Ultra is always the best. And so super excited about the latest A3 Ultra instances which have 8 NVIDIA H200 GPUs. But what I've highlighted in yellow here is, again, remember I said it at the beginning, the most important or the key parts of a high performance computing system is the interconnect. Back when Jay and I worked together, it was 2007, 2008, to build the Ranger supercomputer at TAC, 7th largest supercomputer in the world. It used Mellanox InfiniBand technology. And again, at that time, of course, GPUs were not commonly in use. It was a CPU system, but InfiniBand was used then. So Mellanox, now part of NVIDIA the last 5 years, has been building high performance networking for many, many years. Google's earlier instances use Google's own TCP/X communication in NIC. Now, TCP/X is very good, one of the best networking for normal compute. And in fact, Google even worked with us to implement GPU direct RDMA using their TCP/X NIC. So why with A3 Ultra did they switch to ConnectX-7 networking from NVIDIA/Mellanox? Well, for the same reasons that the Texas Advanced Supercomputing Center back in 2008 used Mellanox networking. Now, of course, today, the ConnectX technology isn't used only with InfiniBand, can also run the standard Ethernet protocol. So what does that mean? What's some of the improvements in performance here? Again, these instances are available today with Google Kubernetes Engine support. You get 2x the GPU to GPU networking bandwidth. But of course, simply networking bandwidth, simply measuring flops is not really good enough. You have to look at the overall performance. And again, Nickel is the software that goes through and ultimately does that lowest level of the network stack. And these slides are a little bit confusing, but these are two different curves here. And what this shows is your Nickel all-to-all performance for passing a 2 GB message between different nodes. And this shows two different tests. The top is showing your highest overall bandwidth, and the bottom is showing the average bandwidth across a number of different runs, 7 different runs, by changing the Nickel parameters. And the point here is that if you work with, if you're using a system that you've installed yourself on another cloud provider, and they haven't gone through and fine-tuned the Nickel parameters, they're using the sort of out-of-the-box generic settings for Nickel, your performance may vary greatly.
Right. Mark, thank you very much for expanding on that. That was actually the question that I was going to lead with, was to ask you to talk about precision in that. And thank you very much for this presentation. We got a flurry of questions in the last few minutes, so I'm going to pick just a few and then save a couple of minutes at the end to talk about some upcoming presentations, including two that you've alluded to in this. One is from the Google Quantum AI team, and one is from the Google team behind GenCast, which is doing exactly what you just said, using AI to help accelerate weather forecast models. So, but let's jump into the questions for this session. I'll give you the real quick, two of the easy ones right away. Are there any specific certifications or training programs offered by NVIDIA that you would recommend for aspiring HPC architects?
I would recommend going and looking at the NVIDIA Deep Learning Institute. It's online. The back end of it actually runs on GCP. So when you take that class, NVIDIA is sending some dollars GCP's ways, and you say, well, no, Mark, you answered the wrong question. It's not about, I don't want to learn about deep learning. I want to learn about CUDA. I want to learn about HPC. Well, of course, once you get that name on the building, once you name the school, you often add curriculum and you don't change the name. And so NVIDIA's Deep Learning Institute has curriculum not just on how to use NVIDIA GPUs for deep learning, but in CUDA and in other tradition, and in quantum computing using cuQuantum and HPC. So that's one of the best ways. But again, a ton of different tutorials available online. NVIDIA's AI blueprints in our Omniverse blueprints. So, gee, I'd like to create a chatbot, right? But, well, in NVIDIA, of course, has NVIDIA Inference microservices that help you do that. But a chatbot may need 10, 20, 30 different microservices. So our AI blueprints are a way to go through and give you sample code, actually a demo that you can go off and run on GCP. And it's a great way to get started building an application.
Mark, I'm glad you brought up that point, that Deep Learning Institute doesn't mean just deep neural network deep learning explicitly, but really is a broader set of learning about different topics in advanced computing. Related question, maybe this is one for Jill. Would you please elaborate on the NVIDIA on Google Qwiklabs roadmap? So what kind of content can our community expect to find about NVIDIA and Google Qwiklabs?
Yeah, so Jay, I've got a couple of partners on my team, and we've worked to build some of the sort of topmost asked for curriculum into Qwiklabs. So I think we'd love to collaborate together with the HPC team at GCP and see if there are some particularly interesting topics. We're working on some work streams right now and would love to expand that to this community.
Great, thank you. There's one final question related to that can maybe be quick. Do Googlers get any complimentary training in the Deep Learning Institute?
We've done some of that, Jay. I think that would be if you have a question from a Googler, just send them to me. And again, my teammates who are working on a lot of these labs and, that type of thing for customers, we can probably quickly answer that for them.
Okay. Yeah, I'll just add a little bit. In the Deep Learning Institute, there's a variety of curriculum. It includes both instructor-led workshops that are run online or in person, as well as self-paced training. A lot of the self-paced training is available at no cost. One of our most popular right now, no-cost self-paced trainings is our introduction to generative AI.
Great. Next question, and we probably just have time for this one more before we make final announcements. Frederick Molina says, is there significant market demand for hybrid AI/ML deployment strategies, specifically those involving training and tuning in the cloud and deploying models on premises, or vice versa, he says? Are we seeing strong interest in architectures that integrate cloud resources such as GCP with on-premises DGX?
Mark, I could answer that, or you could answer that. What do you think?
I'll take a cut at it. I think every organization, right, has their own strategy for hybrid multi-cloud. I don't know any, I don't know any large organization that buys 100% of their servers from Dell. And most large organizations, even if they have, a many $million contract with GCP, probably run some stuff on another cloud. And this is really the beauty of how NVIDIA works with GCP, right? Our NVIDIA inference microservices, all of those SDKs, NVIDIA AI Enterprise. It's the same exact stack that you can get on GCP as well as getting on-prem. So if you write to those NVIDIA microservices and write to those NVIDIA SDKs, you're guaranteed that your application is going to run across on cloud as well as on-prem.